you can form a leftist heap from a list in linear time. Actually, you can form a list to leftist heap. We have a template already, namely fold R of insert empty heap. Right? You have a list 1, 2, 3, 4, 5. You first insert 5 in the heap, then you insert 4, 3, whatever. You insert things in whatever order, and you can maintain this leftist thing and balance and whatnot. You can do that, and that would take order n log n time, because there are n elements, and as you add more elements, the height, the size will become n and the height will be log n, and so this thing will take time order n log n. But actually one can do a cleverer implementation of heaps. You form a leftist heap from a list in linear time. That's very important, okay, and let's see how to do that. So the strategy is to create a size balanced leftist tree, okay, and then restore heap property. This is what you first create a tree without worrying about heap property, and then you restore the heap property. I know that size is balanced, I need to just restore the heap property by rearranging the elements. So the structure remains the same, which means that it is size balanced, but size balanced actually, which is actually more than what you want, okay. In a size balanced leftist tree, I will actually have the left subtree will have size at most, size equal to right subtree. In fact, I should write it more precisely. Size of right subtree is less than or equal to size of left subtree is less than or equal to size of right subtree plus 1. Okay, that is what size balanced means in this case, which is much more than what you want, but you can create such a thing. We know already the smart create tree that we have that does so much work. You can do that. After having done that, you restore the heap property. We will see how to do this all in order n time. So creating a leftist tree is just the linear time create tree that we have already seen. Yeah. So just to recall, it is first of go of length L of L, where go 0 of xs is nil xs, go n of xs is actually node, you have to say size n, and root is y, and you have left subtree and right subtree, comma z's, where right. So this is the thing, and this takes order n time. We know how to do this. So since create tree produces a size balanced tree, the height is already log n. The height is log n. Okay, let's keep this also. And yeah, so this will, instead of calling it create tree, I'll call it leftist tree, and I do this. This is the same code as earlier. Okay, and at every level I maintain the height, the size, this n here. Okay. Okay. So now once I have a tree which I have created in order n time and whose height is log n, I need to show you how to repair the tree and make it into a heap. What does it mean to repair a heap? Okay. So now suppose I have a heap like this, a purported heap like this. So this is a heap. Let's assume that this is a heap. Satisfies heap property. Y is greater than or equal to everything in T1 and everything in T2. T1 is a heap, T2 is a heap. So that's what it means. This is a heap. let's say there is a violation of the heap property at the root. How to ensure that the tree rooted at x is a heap? If x is greater than or equal to max of yz, all is okay. You don't need to do anything. Okay. Else, you have to swap x with max of yz. So let us say z is max of yz. So you will swap x with z. And you can put z there because z is anyway max of y and z. Z is already greater than or equal to y. So you can always put z in place of x. And x can come down and it is still fine because x was okay. So now, but now there is a problem because x could be now if you do this, after this the left heap is still a heap, left subtree. Right subtree need not be a heap. Even though T3, T4 are heaps. Why? Because your x could be so small that it is not only less than z, it is also less than some elements in T3 and T4. So you'll have to keep push x in, you have to sort of sift x down. X is a small element, it has to keep coming down till it finds its place. Yeah. So the heap property is satisfied at the root. Here x is greater than you made this z is greater than or equal to y, z is also greater than or equal to z, x. So at this point it is fine, but the problem could be at the right subtree, rooted at x now and having T3 and T4 as its subtrees. The left subtree is untouched, but the right subtree may no longer be a heap. So you have to recursively repair it, and this is called sifting. Imagine that you have a sieve or and then you have some sand or whatever, and you keep on shaking it, all the lighter particles will go down, and maybe there is another level sieve. So you keep on shaking that, so you are separating these into various levels. So the smaller things will go down till they keep going down. Imagine that there are lots of sieves, you will keep on going down till you find your place. Okay, so that is the point. This is sifting. Okay, so now badness tells you how the heap property is violated at the root. Maybe the heap property is violated because first of all, no bad means nothing is bad. Left bad means that x is less than or equal to the maximum of y and z, and y is the maximum of y and z. Right bad means that x is less than or equal to the maximum of y and z, and z is the maximum. So left bad, right bad tell you whether you want to swap your x with the left child or with the right child. Okay, so that is badness. I can create a new data type called badness. It has only 3 values, 3 constructors, but they are just 3 values. It's like an enumerated type. No bad, left bad and right bad. And I can calculate the badness for a given heap. So badness of any heap node with root x and HL and HR, if x is greater than or equal to max of yz, then it is no bad. Otherwise, then it means that x is less than max of yz. If y is greater than or equal to z, then you say left bad. Otherwise, you say right bad. Where what is y and z? If HL is y is the root of HL, but HL could be nil, in which case you would just take it to be x itself. And z is the root of HR, provided that HR is non-empty, otherwise you just take it to be x itself. Okay, it will be fine in these calculations because you are just checking that x is greater than or equal to max of yz. Yeah, and it is okay if y or z is actually equal to x itself. Okay. This is a constant time operation because you are not doing any recursive calls or anything. You are just comparing the root node with its children. That's all. And its children, and you are extracting the root of the child, and that is nothing, right? That is just a simple operation. So to restore the heap property, I need to exchange the root with either the left or the right child, right? I mean, I could either need to exchange with the left or the right child. Exchange left means I originally have node some size x, x is the root. I have my left child which is node size of left y, HLL, HLR, which are the subheaps of the left heap, and HR, which is the right subheap. And now what should happen? I should swap y and x. So size remains the same. Instead of x, I have y. and I have the same node SL, X, HLL, HLR. So there is nothing at all, nothing changes except Y and X get swapped, that's all. Okay. Similarly, exchange right means nothing else happens except X and Z are getting swapped. Okay. Okay. Okay, fine. Now, sift, where I have to sift a node down, 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 down till it reaches a level where it is greater than or equal to its children. Okay. Sift of nil is just nil because there is nothing to sift. Sift of H is case. So, in all cases, you do a sift if the root violates the heap property. So, you check what badness of H is. If badness of H is no bad, then you just return H. There is nothing to sift. If it is left bad, then what you will do is you will first exchange the root with the left child, and that will give you this. After having exchanged with the left child could be bad, so you have to do sift HL. Okay, this is the point. You first do an exchange and then you do a sift. So node S, X, HL, HR is exchange left of H, and after having done the exchange, you sift HL if necessary. That's a recursive call. Right bad means you do exchange right and then you do node S, X, HL, sift HR. After doing the exchange, you sift the right subtree. Okay. So that is it. So how many recursive calls there are? So you are at the root, you will do a recursive call to your HL or HR. You will do a recursive call to its child, its left child or right subchild. So it will be overall some path down the heap. So it's some order height of the heap, and order height of the heap is log n. Yeah, so that we have maintained because it's a leftist. No, we have not maintained that. We are not because this is a we originally started out with a perfectly balanced tree and height was log n, right? Okay, as we will see now. Running time is order height of the heap, but it is a size balanced tree, so the height itself is log n, so it's order log n. Okay. So, right. So, this is what happens when you have an imbalance at the top of the heap, and this heapify is a, so earlier what we saw was just sift. Okay. Sift works only when there is a badness at the root of the heap, but in general your badness might happen anywhere, right? Somewhere down in your subtree you might have a node which is less than one of its children. So you have to recursively do this sift in some sense. So heapify of nil is nil. Heapify of node Sx HL HR is you first heapify HL, means convert HL to a heap, because your so this is not a heap. So your transforms a tree into a heap, not a heap already. Because when we did the sift, our understanding was that sift is sift works when remember we did all this calculation for this is a heap, this is a heap, and the badness is only at the root, and then we are doing this calculation. But it might, how do you make sure that the left subtree is a heap? You have to recursively call heapify. You have to recursively call heapify for the right subtree, and then once you have changed them into heaps, now you sift the root down to its proper position. Okay. So that is heapify. Okay. Heapify of node Sx HL HR is recursively heapify HL, recursively heapify HR, and now you have a node Sx, sift it. Okay. And finally, create heap is nothing but do this leftist tree and then apply heapify on it. Okay. Yeah, because remember when you do a leftist tree, there is no guarantee that only the root has a badness. Wherever you could have a badness wherever. Now, this is the point that we have to prove. Applied on a size balanced tree, heapify takes order n time. This is what this requires proof. This already takes order n time. We have seen enough times, right? So therefore overall create heap takes order n time to create a heap from a list. Okay, now let's prove the order n time complexity on the heapify of size balanced trees. What is the important property of size balanced trees? The size is n, height is somewhat like log n, let's say 2 log n or something. Okay, that is the property that we want to use. So on size balanced trees, choose some constant c such that t1 is less than or equal to c. What is t1? T is the t1 is the time taken for heapify on a heap of size n. And size balanced tree, so height log n. Log n or log n plus n or some small variant of log n. Right. So you choose c such that and Tn is less than or equal to c log n plus 2 of t n by 2. Why is that? Let's go back here. Okay. So for heapify you make two calls, one to heapify HL and heapify HR. Because it's a size balanced tree, this, if you take the time for this to be Tn, the time for this is Tn by 2, the time for this is Tn by 2, and for shift you require order log n time, because if you go back, see, for shift you try to do shift at the root and then you do it at either the left child or the right child, and its left child or the right child, so it's some log n time. Okay, shift takes log n time. So therefore what I can do is I can choose some constant c such that t1 is less than or equal to c and tn is some c log n plus 2t n by 2. Okay, this is the recursive calls, two recursive calls on subtrees each of size less than or equal to n by 2. Each are of size less than or equal to n by 2 because this is size balanced. Okay, otherwise this wouldn't work. Now for simplicity I will let n equal 2 to the k, then what I have is 2 to the t of 2 to the k equals c of k, which is c of log n, plus 2 of t 2 times t of 2 to the k minus 1, because n by 2, 2 to the k by 2 is 2 to the k minus 1. Okay, but this is nothing but ck plus 2 of, let's expand the recurrence, 2 to the k minus 1 should be, t of 2 to the k minus 1 should be c times k minus 1 plus 2 times t of 2 to the k minus 2, but I can multiply 2 inside, so I will get ck plus 2ck minus 1 plus 2 squared, yeah, 2 squared t 2 to the k minus 2, right. So ck plus 2ck minus 1 plus 2 squared t 2 to the k minus 2, but I can expand 2 to the k to t of 2 to the k minus 2 again. If I do that, I will get c times k minus 2 plus 2t if I expand this, I will get 2 squared times, this is equal to c times k minus 2 plus 2t of 2 to the k minus 3, and so on it goes. But here what will be this pattern? It will be ck plus 2ck minus 1 plus 2 squared ck minus 2 plus 2 cubed t 2 to the k minus 3. If you keep on going like this, it will be ck plus 2ck minus 1 plus 2 squared ck minus 2 plus 2 cubed ck minus 3 plus so on till you will reach some point where you will say, oh, 2 to the k minus 1 c k minus k plus 1, because k minus 1 is k minus k plus 1, plus 2t 2 to the k minus k, but 2 to the k minus k is 1, right. At that point you can replace t of 1 by c, right. So, let us expand this step. This will be 2 to the k minus 1 and you multiply it, that becomes 2 to the k. 2 to the k times t of 1 is 2 to the k, that is this 2 to the k here. And 2 to the k minus 1 times k minus k plus 1, that is what you have here, and c is the overall, because 2 to the k is, 2 to the k times 1, and c is the common factor which I have taken out. So, I have c of c multiplied by k plus 2 times k minus 1 plus 2 squared times k minus 2 plus dot 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 2 to the k minus 1 times k minus k plus 1 plus 2 to the k. I have something like this. Okay. Let us simplify this even further. Right, I have this 2 to the t of 2 to the k is c times k plus 2 times k minus 1 plus 2 squared times k minus 2 plus dot 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 2 to the k minus 1 times k minus k plus 1 plus there is a 2 to the k sitting somewhere, leave it. Now multiply this whole thing by 2, what will happen is that this will become 2k, so I can put that 2k here instead of putting it here, I will put it here, and 2k is nothing but 2 of k minus 0, so I will put it here, and this will become 2 squared into k minus 1, so which I will put it here, and so on and so forth. You see that when I shift, it will become this power of 2 times, if it was k minus 1 there, it will be k minus 0 here, it's k minus 2 there, it's k minus 1 here, and so on. Here it's k minus k plus 1, here it's k minus k plus 2, plus if I shift this is nothing but 2 to the k minus 1, but if I shift, because I am multiplying by 2, that will become 2 to the k, so that will come here, and this 2 to the k will become 2 to the k plus 1, so I will keep all this here. Now I subtract 2t 2 to the k minus t of 2 to the k, so I will subtract all these elements, so 0 minus k, it will become minus k, 2 k minus 0 minus 2 k minus 1 will become 2, this will 2 squared of k minus 1 minus k minus 2 will be just 2 squared, and so on and so forth. So, I have a minus k plus 2 squared dot 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 plus 2 to the k minus 1 plus 2 to the k plus 1 extra 2 to the k, but what I can do is I can actually take this portion and right, 1 plus 2 squared plus whatever till 2 to the k minus 1 is 2 to the k minus 1, and this is just 2 times all that, so it is 2 to the k plus 1 minus 2. So, that is the summation here, this is just summing the GP. Geometric progression. Okay. So, now I have a 2 to the k there. So, but minus k is minus log n, because n is 2 to the k, so k is log n, so this is minus log n. 2 to the k plus 1 is 2n minus 2 plus 2 to the k is n. So, overall I have some c times 3n minus 2 minus log n or whatever. I can ignore all the lower things and this is some 3cn, but overall it is order n, right. So, this is beautiful. I am shifting down, I have to recursively do heapify on the subtrees and then shift the topmost element down. So, but still overall because of this calculation, so your recurrence is 2t n by 2 plus log n, but even that turns out to be order n. Okay. So, this is the main point, and this was all just some high school math. You have to recognize some patterns and do some high school math, that is all you need to do in this. Okay, great. So, I have time complexity of heapify to be this, and yeah, I can do various things. I can do a sort of a heap. I can, given a heap, I can sort it, not just print things level by level or whatever. How do I do it? I will say go of nil is empty list, go of node sx hl hr. I know that x is the largest element, I will put that and I will do a heap union of hl and hr and I will do go on that, which means that it will print the next highest element, etc, etc, etc. So, and then that would be the reverse, and then finally I will do a reverse of it. So, that will be the sorted order. And finally, I can start to the list, create a heap and then sort the heap, and that is called heap sort. Okay. Heap sort is a very important sort. In imperative languages, with in place with mutation, let us say, with ability to modify stored values in yeah, and in imperative languages typically you would work with just work with arrays. But never mind, in Haskell also you can do complexity wise a very efficient heap sort. So create heap takes time order n, sort heap takes time order n log n, because yeah, yeah. Yeah, both sort heaps takes time order n log n, because you have to you do heap union many times and assume that both heaps are of size at most L, then the rightmost spine will be log n, and heap union goes via the induction on this thing on the rightmost spine, and therefore your n times you will be doing a log n operation. Okay, so that's why it's log n, and that is it about heaps. Okay, so this is a very nice data structure, priority queue data structure. It is very useful in certain algorithms which require priority queues. Versions of Dijkstra's algorithm. Okay, so that is it about heaps. I shall now show you how some of the I shall now run some of these and show you how it works, and that would end the lecture. Let me go to VS Code now. Okay, I have here a heap.hs module. Let's see how it is. I have implemented all these things. You see, heap, empty, heap is empty, etc., etc. The heap data structure itself is heap a nil node int a heap a heap a. This int is the size. I have various things. You see, size is just extracting that component from the node, and then I have is heap. I have realign. I have heap union, insert in a heap, find max, delete max. All these things which are shown in the slides. Leftist tree is that smart create tree, and this is that sift. Okay, I look at this badness and I do this exchange left, exchange right, and sift will, depending on what kind of badness it is, it will either exchange with the left child or exchange with the right child and then sift. Heapify is this, and create heap is just leftist tree followed by heapify. Sort heap will actually sort the elements of a heap, and heap sort is create heap and then do a sort heap. I can just show you, just so that you can visualize this. I can do a create heap, and I can just say 0 dot dot 20. Yeah, you can see how it is, right? 20 is at the top, and this is a leftist heap, as you can check, because right, and it is height balanced. 20 is at the top, its children are 9 and 19, right? And children of 9 are 4 and 8, children of 19 are 15 and 18, children of 4 are 1 and 3, children of 1 is 0, children of 3 are 2, children of 8 are 7 and 5, children of 7 is 6, 15 has 12 and 14 as children, 12 has 11 as a child, 14 has 13 as a child, etc., etc., right? You can see this. You can also try to see what happens if I try to, for instance, insert 33. It insert in heap 33 it, let's say, right? Oh, this case why does it not care about the height balance? Yeah, there is no need to care about anything because the 33 has right child which is nil, and all your properties are still true, right? The rightmost spine here is of length 1, and you don't necessarily want height balance or size balanced or anything, right? All you want in an insert in a heap is that the size of the left heap is greater than or equal to the size of the right heap. That's all. But if I delete something like if I do delete max, here there won't be any problem. Yeah, I get 33 and then this other thing, so I can actually do delete max of second of it. Right now, I actually, you see, 19 has been promoted to the root, 18 and 15 are its children, and you are trying to merge the yeah. So right, so you are always merging the so 9 is a tree, right? 19 has its right. So why did this happen here? Why did it so happen that 9 becomes the child of 16, etc.? Because of realign. Okay, so you are trying to merge. So what you are doing is that you have 19 here. Its left child is, its left subtree is 15, 12, 11, 14, whatever, this thing. Okay, and notice that that has just gone to the right here without being disturbed. What you are doing is you are trying to do a union of this tree 9, 4, 8, that tree with this tree which has 18, 17, 16, 10. And after you do the union, you will after you have done the union along the right spine, you will keep doing a series of realigns, which is why it has happened like this. See, and you have a this thing. So if you try to do some other union, then you will go along the right this thing. But you will do a realign which will switch these elements around. Okay, so I invite you to play around with this and have fun with heaps. This is a very important data structure. I shall stop with this now. Okay, thank you.